Just as we did with studying linear motion, when we're studying angular or rotational motion, we need to focus on some quantities to describe that motion. Just as we started out with linear motion, we'll start out with angular position, which in this case will be, you will use the symbol theta to represent the angular position. Angular position is measured in radians, RAD for short, but sometimes we'll use other units, such as revolutions or degrees. You are required to know the conversions that 360 degrees is equal to 2 pi radians, or that 1 revolution is equal to 2 pi radians. This is a fact that I expect that you'll know, and thus you will not be given this fact on a test or quiz. We know that displacement is the change in something's position. So since we have an angular position, we can also talk about something's angular displacement, or delta theta. We'd calculate this by doing the final position minus the initial position. Another quantity that we can find about something that is rotating is its angular velocity. We use the symbol omega, which is a lowercase Greek letter, as you can see on the screen here, to represent angular velocity. Much like with linear velocity, angular velocity could be instantaneous or average, instantaneous being at a set point in time and average being over a time period. Its units will be radians per second. Sometimes we'll see other units such as revolutions per minute, which you can see symbolized as RPM, or rev per minute. And you should know how to convert these using that conversion factor that there's 1 revolution in 2 pi radians and 60 seconds in a minute. Lastly, we'll talk about something's angular acceleration, or the rate at which its angular velocity is changing. Again, we can have average or instantaneous. And the units that we'll use here are radians per second squared. For the most part, these are the only units that you'll see with angular acceleration, although rarely you could see revolutions per minute squared. Now, if we think back to when we studied linear motion, we started out with a constant velocity, or CVPM. If we have a constant angular velocity, we can use an equation very similar to what we did with linear motion, saying that the average angular velocity is equal to the angular displacement divided by time. Once again, this only works if angular velocity is constant. If instead we have an angular acceleration, so the angular velocity is changing, we'll use one of these 4 equations. Now, these equations should look somewhat familiar to you, even though we're using different symbols. And that's due to the fact that these are literally the exact same equations that we studied in our constant acceleration unit, except we've input the rotational or angular symbols rather than the linear symbols. So anywhere in those equations that you saw an A, we now see an alpha. Anytime in those equations where you saw a V, we now see an omega. One last important step, or important fact, is that just like their linear counterparts, angular quantities have direction. For the sake of this course, we will use clockwise or counterclockwise as their direction. And just as in math class, when we think about the unit circle, counterclockwise is considered to be the positive direction, whereas clockwise is considered to be the negative direction. We'll have some practice in using these equations, and then of course we'll also look at how these equations can help us learn some things about an object's rotational motion.